putting everything together that you have learned so far. Here it is, kinetic energy, the change in kinetic energy is half mvf squared minus half mvi squared. That's what you've done, right? The change in kinetic energy is this. Now, if it started with a zero velocity, the change in kinetic energy is just going to be half mv squared. Or, if you want to know the kinetic energy of an object at a certain moment, all you need to know is how fast is it moving. So just say half mv squared. So this will be the instantaneous kinetic energy at a certain spot. Do you get it? Like at this particular moment, it's moving at this speed. It has this much mass. What should be its kinetic energy? So just directly throw that in. But if you're checking out how much is the change in the kinetic energy in a certain process, then you have to do it properly by subtracting the final minus the initial kinetic energies. That is change in kinetic energy. And the other thing we did was a change in the GPE, which is mg times the change in the height. Now, if the change in the height is negative, that means it is losing its GP. If the change in the height is positive, then it's going to gain. And then we did elastic potential energy. Elastic potential energy is half kx squared. Now, all the background I gave you about springs was just to get you to that equation. Because if I throw this equation straight away and say, all right, take it for granted, this is an equation for elastic potential energy, it will be like, I don't know how this equation came from, where did it come, what is K, you have no idea. So what is K actually? For every spring, force is going to be proportional to extension within proportionality and elastic limits, right? If you don't exceed limits, then it should be always a straight line. And that's why we say F is proportional to X.
So K is the line. K is...
No, K is the slope of the line.
Okay.
The slope of the line is K, because it's like Y equal to Mx and that sort of thing. So F is equal to Kx. Think of this as Y is equal to Mx plus B. What is the intercept?
0.
0, because when there's no force, there's no extension. So in this case, B is nothing. So it is only this one. So K typically is the slope. Now, if it is a very stiff spring, like a car spring, this is going to be extremely steep, indicating K is big. If it's a slinky sort of thing, it is going to be flat like that. That means even with the smallest force, it's going to be stretching pretty well. Do you get it? So different springs are different, but each spring has the so-called force constant or spring constant. Sometimes they use spring constant if they know it's a spring. If it is not a spring, but if it is just a rubber band or something like that, then you can't call a rubber band a spring. Then you use the term force constant. Or sometimes they'll say force constant of the spring. So anything is okay. So in this case, what is K equal to? F over X. So the unit of K is Newton per meter. Newton per meter is the unit of K, the force constant. So when you're going to use this one over here, the K over here, make sure that it is given as Newton per meter, not Newton per centimeter. If you are given Newton per centimeter, then no, that is not K in our proper units. So you've got to change it. How do you change? So if I say 100 Newton per centimeter, what is it in Newton per meter? Really? For stretching 1 centimeter, I need 100 newtons. For stretching 1 meter, you see how the mistake is coming up is because conversion. You're jumping to the conclusions because centimeter to meter, and you know the number is 100. So you're kind of directly like dividing it. So I'll show you what to do. And again, I have done this before. 100 Newton per 1 centimeter is equal to how many Newton per meter? Now you're going from centimeter to meter. Unit is going from small to big, so the number should go?
Big to small to big.
What? The unit is going from small to big, and the number should go from Big to small.
Yeah.
It should go smaller. So there it is. And Newton, that's fine. Now put this together. What is it?
10,000.
Okay. So be careful when you're changing Newton per centimeter to Newton per meter. Very common mistake if you're not converting properly. Or think practically. For 1 centimeter, you need 100 newtons. So for 1 meter, you need 100 amps. Make sense? Okay. So that is the force constants unit. That is the force constants unit. And X is the extension in what unit? It should be meters. That should be in meters. That should be in Newton per meter. Only then your elastic potential energy is measured in joules. All these, any energy form is joules. Work done, joules. Everything is in joules. So this is something that we have come across now. This law, which is F is proportional to X, is called Hooke's law. Just for the for the knowledge sake. We will do that later on when we actually touch up springs, especially for the lab. But then right now, this is called Hooke's law. The proportionality between force and extension. Is this part clear? Mm-hmm. And the other thing that you've done is work done is force times displacement and maybe the angular component. You've done that. And force can be, work can be positive, can be negative, can be nothing, right? Yeah.
Isn't X displacement in all the other equations?
Yes.
So why do we use D in that one?
Where is D?
And W equals FD cosine 0, cosine theta?
You can use any letter. But a very commonly used term is D for displacement in work. I mean, just to kind of differentiate. Just to differentiate. When you think about work, every book literally says FD.
Okay.
And that kind of differentiates the other topics clearly. Now, FX can be confused a little bit with some of the topics. But when it comes to FD, you naturally kind of link it to work. All right, so yeah, you can use any letter, X or Y or whatever you want. As long as you understand what it means, that's fine. Yeah.
You said that everything's in joules, but force is still in newtons, right?
Yes, force is in newtons, but this is meter.
Okay.
And work done is measured in Newton meter, which is the same as joule. Good. Newton is here, and this is meter. Product of Newton and meter is joule. So as long as you have the kilogram meter square second to the power of -2, as long as you have that, then that is joule. Okay? As long as you have that one, that is joule. Now, what is? Can we use this one? Can you take that part? Take MGH. What's mass measured in?
Kilograms.
Kilograms. What is G measured in? And what is delta H measured in? Is that the same as that?
Yes.
So it is joule. Now let's take this one. Half of V squared. What is mass measured? Half, no units, right? S kilogram. What is velocity? Meters per
second.
square it. So meters per second and then square it. Is that the same thing? So that's why it's joule again. So that's, you can see that all these equations will lead to this. That's why it is all measured in joules. Okay? We will go through a bunch of problems after this. So the next concept is power. Power is the other, it's not that difficult. Power. Power is the rate at which work is done or energy is expended or used. The rate at which work is done or the rate at which energy is produced or used, or in any manner you can take it. It is a rate, which means divided by time. So power is work over time or energy over time. So what's the unit of power? Energy over time. So what is it supposed to be? Joule per,
Per second.
and this in basic terms is what?
Kilogram
Kilogram
times
meter square.
Times second to the negative first.
Negative 3 because there's another second coming in the denominator.
Yeah.
So you have already this one and then divide by one more second. So that second also will go up and become minus 3. So this is the SI base units of power. Instead of writing joules per second, we have a shortcut unit for power named after James Watt. W. Okay. So joules per second is shortened as just watts. So power is measured in watts. You know that any power, sound power, you're measuring in watts, right? If you have an amplifier, you say, oh, this is 300 watts. What are you telling over there by saying 300 watts? 300 joules of sound energy or any energy is produced per second. It's a rate. Rate at which energy is used, that's power. You have light bulbs, you have television, some of them are higher rated powers and some of the lower rated powers. Now, if you're taking a lower rated power, that means you're not spending much energy per second, right? So every electrical device should be rated in terms of power. Everything, your monitor, your computer, anything. If you look at the label behind, it will tell you important information like how many volts it will operate on and how many watts. How much energy is going to consume. Yeah.
Why don't we use volts in any of these?
Volt is a different thing altogether. We'll see volts towards the end of the year. Yeah, we'll see about volts at the end of the year. But watts is simply energy per second. Volts is more related to the electric potential energy, right? Yeah. We'll talk about that later. Now, what is the electric power rating of this light bulb? What do you know it? Just don't look there. Tell me. Do you have any idea?
30 watts.
Close. Now look. Look what's written on it.
Wow.
You'll see where it says Phillips or whatever.
It's over there.
It's
30 or 32 watts.
32 watts. You see it? You can stand up and look from different angles.
Get on the chair.
So power rating is something that you'll see on all devices, and that is what it means. Power is number of joules per second, and so the energy or work is equal to power times time. Is that clear?
How do you find, how would you tell the difference between if someone's writing work or watts?
Oh, if it comes in the form of an equation, that is work. If it comes as a part of a unit, that's watts.
Yes.
Yeah.
So if you've got a light switch with like a dimmer on it, is the dimmer really just changing how many watts the bulb is using?
The olden days dimmers, they did basically nothing. Just they have a bunch of coils inside, so the current passes through those coils, and the coil will get heated up, and it kills the power from here. So the bulb will get less power. So it will do the dimming action, or the fan controlling the speed of the fan. The olden types, the old regulators, they're called regulators. They had resistances. So when the current was going through the resistances, it spends more energy here, but overall energy is the same thing. But these days, the dimmers that we have, they're all solid state. Solid state means more electronic type. So what they do instead is it takes 110 volts and then it reduces the voltage itself and then sends just a little voltage for it to operate. So it controls it in the form of voltage, and so you're saving power.
So what does it do with the rest of the voltage?
You can actually drop off the voltages by different methods. Like, you have adapters, right? to charge a phone.
Yeah.
The phone requires only 3.6, 3.7 volts to charge, but what you have is 110. So we use transformers and we use solid state methods to get lower. And that way whatever you are consuming in the phone is what power is taken from there. The power consumed from the wall is exactly the same as what is needed by a phone. So you save a lot of. That's why if you plug that adapter in and you just forget about it for months, it is not going to charge you anything because it uses hardly any power. So maybe for a month or two, you may spend 1 cent. Yes.
Why do they have both AC and DC current?
AC and DC. AC is something that is more. AC means alternating. You'll see that again as we go to the end of the chapters. You're going too far ahead. Right now we are okay. Anyway, I'll answer the question. AC is alternating current. The current is not fixed in one direction. Like the current goes this way and then backwards and then this way again and back again, and it cycles 60 times per second over here in US. 60 times it kind of rocks itself, going back and forth. That is what's happening here. But whereas DC is a direct current, like the current that comes out from here when I use it for lighting up something is a direct current. Current only goes from the positive and comes back to the negative. It's only going one way. So that is one way. Now, DC is what is used in most appliances. So how the TV actually operates internally, it's all by DC. Everything is operating by DC. But then what we are getting over here is 110 AC. And what you have to do with that AC is the AC goes into the television, and there are transformers and stages where they can actually break it down to 12 volts, 3 volts, 6 volts, 8 volts, as per needs to operate all the different circuitry, but they're all going to be DC. Now, what is the problem if we get DC over here? DC is something that cannot be stepped up or stepped down. It's so difficult. It can be, but it's so difficult. DC cannot be stepped up or stepped down so easily. AC can be stepped up and stepped down so easily using the so-called transformers. That's a transformer. So when you plug this into AC, you can actually get, this is a transformer. All right? So you can actually plug this one in to AC 110 and probably get here 12 volts. But it will be AC. So the benefit of AC is actually beneficial. That's why we use AC in our places. Yeah.
So like, if my computer has like a 600 watt power supply, does that mean that like power is moving out of a like wall, whatever, at 600 kilograms?
600 joules per second.
Meters per whatever
Yeah,
square.
I mean, instead of that, you can do in terms of joules. What's 1 joule?
If electricity has
1 joule is 1 Newton applied to a distance of 1 meter. So if I push this book with 1 Newton and I move it by 1 meter, I've done 1 joule of work.
But you're pushing electrons, so it's like almost no energy.
Oh,
Is it?
we are not pushing.
Yeah, that's what. Yeah.
The electric potential energy is doing the job. That's why we're paying. We are paying LG&E because they are providing the potential difference for us to use.
right.
So because they are providing the potential difference, we pay them for providing that. It's like, it's like this. You want this nail to go in, but you stand next to it, it's not going to go in. What you need is a hammer coming down and hitting it, right? Suppose you don't want to do the work of lifting it and hitting it. You need somebody to do the work for you. So you pay someone, all right, can you hit it for the first time? All right, here's the money. Bang. He's finished. Can you do it again? Okay, bang. So he's doing it. Every time he does it, you pay him for that. Nothing comes free in this world, not even a smile. Okay? Yeah. Because if someone is smiling at you,
They're using energy.
no, I mean, there is a reason behind that smile. They are expecting something out of you.
Free smile.
There is something. These days, everyone is so materialistic that if they feel that there is no benefit of smiling at that person, they won't smile. All right, leave that aside. Now let's come on. Now let's work through Here's a problem, and I want you to kind of think independently and just see how you can tackle it. And the problem is this. The problem is right in front of you. This is 1.5 kilogram. All right? Now see what I'm doing to it. I am pushing this book, which is sitting on the table, and I'm pushing this book and giving it a velocity of 2 meters per second. You understand the problem? I'm giving this book a velocity of 2 meters per second. I'm just pushing it and letting it go with 2 meters per second. And what happened to the book is, let's say the book kind of went all the way 1 meter and stopped. Make sense? Then here's the book. 1.5 kilogram is the book's mass. And when I pushed it with a velocity of 2 meters per second, the book slid across like that and stopped. And stopped 1 meter away. And the question is, find the coefficient of kinetic friction. Find the coefficient of kinetic friction. Now see, this is a problem. And you may be wondering, like, what has this to do with work? What has this to do with whatever we are learning right now? Don't give up so easily. What do you have to do first? Draw a diagram. That's why I drew that first diagram part of it. You cannot start doing this problem without a diagram. If you say, all right, what is the equation? I know I know mg delta h, and I know the half kx squared. Which will I use? If you start thinking like that, that won't work. Yes, Cooper?
Yes.
Yeah. So if I'm asking something like this, what you need to investigate is, all right, it was moving at 2 meters per second, then it stopped. Why did it stop?
Friction.
Friction. So you know that there is a frictional force. As it was moving, as soon as I released it, there is a frictional force that is acting on it. Now, how can you find that frictional force? Is your next goal. Your next goal is there a way to find the frictional force?
Yes.
Because force is mass times
Acceleration.
force is mass times.
Acceleration.
Is it possible for you to find the acceleration because you know the initial velocity, you know the final velocity, and you know this?
Yeah.
Can you find it out? Go ahead and find the acceleration. What equation are you going to use?
Yes.
Vf squared. See, you have to go back. You have to go back and fetch the equation that you learned earlier and then come back here. As per needs. That's why I said don't forget anything that you learned in the past because we need them. And I'll show you different ways of doing the same problem. Different ways of doing the same problem. Alright, so Bf squared is equal to Bi squared plus 2Ax. Let's substitute. 0 equal to 2 squared plus 2 times A times 1. So what is the acceleration? Acceleration?
-2.
Minus 2 meters per second square. The minus sign tells you it is deceleration, which means the force is backward. See, you can actually figure out the force is backward because this is a negative sign. You already knew that it is going to be backward, but now it confirms, yes, that force need to be backward. So now, how much is this force? So friction. How much is the force? You know that?
Yeah.
Okay, what are the forces that are acting on it?
Normal reaction.
The weight, how much is the weight?
14.7.
14.7. And what else is acting on it? The normal reaction, which is?
14.7 meters.
Yeah, you know these things are acting. But if this is 14.7 and that's 14.7, and this object is acted on by a force of ma as a resultant force, which stops it. So what is the force? Mass times acceleration. So it is 1.5 times -2, which is -3 newtons. And that means the frictional force is 3 newtons. Do you get that? Now why I'm not putting -3 over here? Because already the arrow is backward. You don't have to put the minus sign. This minus sign tells you the force is -3, which is 3 this way. You know the friction is 3. Can you find this now? What equation are you going to use? Friction is equal to You have done this equation before. Alright, go ahead. So 3 is equal to mu k times 14.7 because you know the normal reaction is 14.7. So find out mu k. How much?
0.2.
0.2? And you can just go back in and see how did we solve it. We solved it by using equations of motion, got the acceleration, got the force, got the equation for kinetic friction, and solved it. I'll show you another way of doing the same thing. Same thing. Alright, taking care of this?
Wait, yeah.
Now let's look at it in a different angle, alright? A different way. What kind of energy does this book have as soon as I release it? Kinetic energy. So what was the kinetic energy here?
0.
No, I just released it. How can it be 0?
Oh, 2.
The kinetic energy here is half mv squared, which is what? Half times 1.5 times 2 squared. How much is that? 3 joules. 3 joules is the what energy? Kinetic energy. What's the kinetic energy here?
0.
So what's the change in kinetic energy?
3 joules.
Be careful. Change in kinetic energy.
Negative.
Negative 3 joules. The change in kinetic energy is negative 3 joules. And what did I say the change in kinetic energy is due to?
Friction.
Work done. Check back again. Work done is supposed to be change in kinetic energy. So who's doing the work here? Friction is doing the work.
Yeah. Okay.
Right? So work done, in this case, is negative 3 joules. And you know the formula for work done is force times displacement. Is equal to negative 3. And you know displacement is 1 meter. So what is force?
Negative.
See, we got to that force straight away. We got to this force straight away instead of using equations of motion. Make sense? So you can go with this line of thought. That is, work done should be the change of kinetic energy. Is this object suffering a change of kinetic energy? Yes, that means work has been done. And now you realize that the work done is negative because it is slowing it down. You see that it's slowing down. So it is negative. And then if you equate it to FD, you find F to be negative 3. So we discover this straight away. You don't have to do the equations of motion or F is equal to ma. You get that straight away. And then do the friction part of it out. Okay. And got it? So the questions or the situations can be completely different. But you need to just figure out how to answer these questions. Alright, here's a piece of wood. That's a piece of wood. And someone is shooting a bullet into it. Someone is shooting a bullet into the wood. And the bullet is moving at 200 meters per second. The bullet of mass 20 grams. A bullet of mass 20 grams is moving at 200 meters per second. And it is hitting this wood, drilling through it, and coming out from here at 50 meters per second. So it's basically going through and then coming out at 50 meters per second. What is the average force offered by the wood on the bullet? What's the average force offered? And of course I would say the thickness of the wood, let's say, is 3 centimeters. The thickness of the wood is 3 centimeters. So my question is, what's the average force offered by the wood on the bullet? So find average force. So inventing a problem or bringing a problem in front of you is so easy. You just think of a practical situation and make it into a problem. And then how you think after that is using your concepts that you've learned so far. So the bullet moving. I'll wait for some time. Can you just... Oh, there's hardly any time. Okay. Go ahead. Anyone has an idea to start with? Yes, go ahead.
You need to find the force of the bullet first.
Force of the bullet?
Force applied by
Kinetic energy of
The bullet is
Yeah,
the
change of the
bullet is
kinetic
going
energy.
at a certain, that means it's entering at 200 meters per second.
You have to find the change in kinetic energy.
Find the change in kinetic energy. That's a good start.
Yeah.
And that change of kinetic energy is equal to the force times displacement, work done. So how much work is the wood doing on the bullet? That's what you're looking at.
So like on this one, would you do 1/2 times mass times final velocity squared minus 1/2 times mass
Exactly.
times initial velocity?
Yep. So half mv square here, half mv square here. Again, don't think of any fixed equation. Look at what's going on. What is the kinetic energy here? Half times mass 20 grams. Will you leave it as 20?
No.
You got to change it to kilograms. 0.02 times 200 squared. Whatever you do here, that will tell you the answer for that. How much is it?
It's two,
I got
2,000?
two, no, two.
Oh, crap. Hold on.
Four?
It'd be 400 joules.
400 joules?
Yeah.
400 joules to start with here. What's the kinetic energy here? Half mv square again, so half times 0.02 times 50 squared.
25.
25 joules? Is that 25?
25.
You wrote 4,000.
100. Yes, 25 joules.
On the left, you wrote 4,000.
Is it 400?
Yeah, that's
I
what
thought so too, yes. Now what is the change in kinetic energy? You can see that. What is the change?
375.
Minus 3.
Minus 375 is the change in kinetic energy is equal to F times 0.03. And then you can find the average force from there. Centimeters. You got to take care of everything. Centimeters to meters, grams to kilograms.
Why is it negative 3, sir?
Final minus initial. Final is this. Initial.
Oh, okay.
Conservation of energy simply states this. Energy cannot be created nor destroyed. It only can change from one form to another. Energy is not going anywhere. It is just changing its form, and that's all it contains. But how do you use them is now something that we have to look into. It's like this, I give you $100, all the coins, and you put it in the pocket and start walking to the cafeteria. You went over there, and then you emptied out your pockets, and you have $80. But you are accountable for what I gave you. So, it has to tally. So, $100 you put in your pockets, and then go there and it becomes $80. You say, well, that's it. No, that's not it. Tell me, account for the difference. Right? Account for the difference. You must be able to say clearly, like, why is the difference? And then you have to come up with an answer saying, all right, somebody stole from me, or the pocket had a hole, it just fell off and I lost it. So somebody must have gained it, right? So you have to give a plausible explanation for the difference. It is not going anywhere, it's going somewhere else. All right, so that is basically the law of conservation of energy. Energy is moving from one form to another form. Later on, next year, the same thing will be worded slightly differently, which is matter and energy together are conserved, not just energy. But for now, energy is conserved. That's it. For now, you don't have to worry about the other part. For now, energy is conserved. Energy cannot go anywhere. It is just different forms. So, if there is a situation given to you, you must be able to figure out from where did it come. Like for example, look at this action of mine, and then let's find out where are the energies. Simple action of this. So, where is the source of all this? For the action that I did, where is the source of the energy? Like, how did it all start?
Chemical energy in your body.
What's that again?
Chemical energy.
The chemical energy, the food in the body is basically being burnt to supply energy to the muscles so that the muscles will start, contracting and all that. So in order to clap, I have to lift my hands, and so muscles have to start working. And muscles are actually controlled by the brain, and so the brain is fed. The brain also needs energy. So brain takes some energy, processes stuff, sends the signals electrically to the muscles to make it flex, and then, the muscles move, and the hand comes here, and now the next thing is some other muscles will make it go. Or gain what?
Yeah, kinetic energy.
Kinetic energy. So before I hit the hands, it was all kinetic energy before it hit. And finally, as soon as I hit, both hands came together and they stopped. So all the kinetic energy is gone. Where is it gone? Sound, heat. All right, sound and heat. And basically, sound and heat. Where is it gone after that? It stopped. Where's this? I don't hear the sound anymore.
It's just spread out.
Spread out to where?
The universe.
Into the air. So basically, I'm disturbing the particles of the air, and the particles of the air are now agitated more than before, which means they are getting heated up. So the particles of the air are going to be heated up because of this agitation, because I'm disturbing them. So the more you disturb them, the more they get agitated, so the temperature of the room can go up. You understand? Yeah, if everyone starts clapping, it actually because people are burning energy to do that, and so it'll all come out into the same room. Seriously. No.
Where's
So-
the screen?
Say it again?
Where's all the screen?
What is that again?
Not
Where's all
as
the
effective.
screen?
Oh, same thing. And any sound energy, any vibration that you produce is actually going into the room. It's not going anywhere else. And it is getting now. Suppose your air conditioner is actually. Suppose your air conditioner is actually operating. What it does is it removes that heat which is actually generated here, and then throws it out. And so now it goes to the outside, and then it's kind of warming the outside part of it. And again, the whole energy concept is there. The earth is receiving it. Yeah.
So what does soundproofing, like big soundproofing panels, how does that change?
Soundproofing channels means like
Panels and walls?
panels which are actually like preventing sound from coming in. Yeah, they're absorbing material, and they could be reflecting it. Multiple things. The main concept over there is we don't want sound to get across. So where is it gone? It could be absorbed as vibrations and then suppressed. It can be anywhere. Like for example, your car's vibrations are all picked up by the tires. It's not sent to you, right? So the tire is basically doing the suffering because it's getting compressed and expanded like that. So the tire is taking care of it. It's absorbing all the energy of the vibration. And so you are comfortably sitting here. If you use steel tires, then you cannot be comfortable. Imagine it's a steel tire. Everything is steel. No cushions, nothing. You're sitting on a steel driver's seat, and everything is steel. No springs, nothing. It'll be horrible. Okay? So, yeah, energy is not going anywhere. It's all accountable. That's what I'm saying. Now, so we said, okay, it's from the food. Now, where is the food coming from? Food is coming from not just animals. It can be from plants. Oh, plants and animals. Okay. Plants and animals. So animals feed on plants. Animals feed on animals. And ultimately it's going to the plants because everything to survive they go there. Okay. and then plants where are they getting the energy from?
From the sun.
From the sun.
Where's the sun get energy from? Huh?
So yeah.
God.
So if you try to trace back, good. If you try to trace back, you'll see that it all leads to the sun. Anyway, the source is the sun. That's what I was reading. The source of all source. The sun cuts off completely, we are all done.
We're already screwed.
Yeah. If the sun cuts off completely, no more energy input, our energy is going to be changed into a low grade energy, and then after that it is all gone. So that back to Ice Age and all those things. Yeah.
Do you remember what year it was that you asked it, or that you were prompted to ask it where Bin Laden was?
I was in Abu Dhabi from 1994 to 2005, so it should be somewhere close to 2000ish.
Yeah.
Around. When was he?
2008.
Yeah.
It was 2010, I think.
2010 or something.
No, yeah.
I was, yeah.
So, say for whatever reason, like somebody's gonna.
No. Wait. When was the
Oh,
World Trade?
2001.
2001. So probably it's after that. I left Abu Dhabi in 2005. So probably after that.
It said he was killed in 2011.
Oh, May
Yeah,
2nd.
probably. But no, the World Trade Center thing took place.
Oh.
So it should be after because that's when everyone was chasing, right?
Yeah.
That's
I mean,
when
that's what I would
that's
ask.
when I was looking at it. Yes.
Down, like chill near the center of the earth, because that's still going to have its heat energy spinning.
Yeah, but the heat energy is part of the Big Bang.
Photosynthesis. Okay, but
Yeah.
even without the sun, could you like not dig down and use the heat?
Yeah, the geothermal energy. Yes, that's what's called geothermal energy. But there's limitation to that. Even that is going to go out. Eventually, that's also going to cool down, and you can't. Like for example, it's like a potato. If you're actually like cooking it, boiling it, when you just take it out, it's super hot, right? And after some time, the surface, the skin, and that area becomes normal temperature. And when the outside becomes normal temperature, you may think, oh, it's okay. Can you poke your finger right into it? No? No, yeah, it's going to burn you because inside, deep inside, it is actually hot. So it's like that. It is still hot inside, but outside looks fine, you know? But after some time, even the inside stuff is also gone. It becomes cold. That's what it is, basically. Earth is just like that. So the outside is now adaptable to human beings, and so we feel fine. But eventually, it's the energy. Now, we are receiving sun's energy continuously, and that's why it's kind of filling it up perfectly and balancing it up right now. So if the sun's energy is not received properly here, then it changes the climates and changes everything. All right, now, what kind of questions are, so what is the energy conservation in general? Energy is going from one place to, so if you have a spring that is pulled and stretched, and then when you release it, the spring is going to transfer its energy to kinetic energy of an object, right? And you saw the homework questions which deals with the same thing. I'm going to ask a question right now. Just see how you can answer it with just thinking about the system. Now here is a football. Now some students complain that I'm using the same marker for football, for gun, for stone, for an atom, for a nucleus, and for protons and neutrons. Everything is a marker for me. Anyway, this is the best object for me. I can toss it, no harm. Yeah, this becomes an helicopter for some time. This becomes a plane sometimes, like that. So this is the way I do. All right, so football. A football player throws a ball at an angle of 30 degrees, and the ball goes to a height of 20 meters before it comes down. Question is over. Again, a football player throws a ball at an angle of 30 degrees, and it reaches a height of 20 meters before it comes down. At what speed did he throw the ball? What do you do first?
Resolve.
Huh? What do you do first?
Draw a picture.
Draw a picture. Before drawing a picture, if you just like ponder over that question, you won't get anywhere. So the first thing to do is draw the picture. So here goes. And here is the thing I told, 20 meters. And here is the velocity with which it's thrown. And here is the angle 30 degrees. This is all I gave. This is the information I have given you. Now, you need to think about solving it. We need this velocity. Now, but just by looking at this, you may be prompted to start your approach by using what method?
Resolving.
Yeah, you resolve it and then make the table horizontal, vertical, right? And then use the projectile motion technique. That's going to take a long time. Look at what's happening here. Between here and here, what kind of energies are getting transformed?
Kinetic and potential.
Okay, so let's take this as our reference level. So what is the GPE here? What's the KE here? At this point, how much KE is there on the football? Zero. Zero. You're tossing it.
You don't know. We don't know.
Okay, tell me an equation at least.
K is 1/2 mv.
1/2 mass of the football times this velocity that I throw, right?
Yeah.
Okay, you have something here. Now, as this ball starts ascending, what is happening? What kind of energy is being gained as it goes there? So GPE at this point, now if the GPE is 0 here, I told you it's never 0 anywhere, but if I take the GPE as 0 at this level, what's the GPE there? MGH, where H is 20. Right? MG delta H, and delta H is 20. Is that understood?
Yes.
Now, what about the kinetic energy here? Is it 0?
No.
No?
It's still moving.
It's still moving forward, yeah. Do you have any idea of that velocity?
Yeah.
Very good. This is V cosine 30. Think of the concepts of projectile motion. Because when you throw it, it has two components. The horizontal component does not. The vertical component changes. The vertical velocity here is 0, but the horizontal speed is still there. So definitely there is a kinetic energy, and how much is it? Half m
V cosine.
v cosine 30 squared. Is that right? And assuming there is no friction on the football, this energy should be equal to this energy here, because energy is conserved, yes. So all you do is just set up this equation from here to there. That's it. So half m v squared is equal to half m v squared cosine square 30, because I'm squaring that, plus mgh. So that's our equation. What can you do now from this equation?
Cross out with on both sides.
Cross on which one?
So like you can eliminate 1/2
Oh,
on both sides.
how do you eliminate 1/2? Multiply through it by
2.
2. So if I multiply through it by 2, this equation becomes,
Plus 2.
is that right?
You can take out an M.
You can just divide the whole equation with m is gone. Now you're left with only some things, and alright, so let me keep this as v squared because I don't know that, and this is what? What is cosine 30 squared? Cosine 30 is radical 3 over 2
Yeah.
squared. 0.75 v squared plus 2 times 9.8 times 20. How much is that? 2 times 9.81 times 20.
It's 392.
392. Okay? Solve this equation. Solve it. Subtract this one here. It will be v squared minus 0.75 v squared is equal to 392. So we have 0.25 v squared is equal to 392. So v squared is equal to 392 over 0.25, which is something. And then you take the square root of it.
39.6.
How much?
39.6.
39.6 meters per second. It is pretty fast for a football. 39.6 meters per second translates to something like 89 or 88 miles per hour. So football going at that speed is probably
Deadly.
not from a human. Probably it's like a cannon. Shoot the ball. Okay? Yeah, normal football, highest speed of football and all that is maybe 55, 60 or something like that, right? Miles per hour. So you see this? How the problem is solved, we are approaching by using energy. Most cases, the energy method will be the easier way to do it. Most cases. But yes, you can go by projectile motion if that is the way you want to go. But projectile motion guaranteed is going to take a long time for this particular problem. Yeah.
Where'd you get 0.25 from?
1 v square minus 0.75.
Okay.
Okay? This is just 1 v square. That's it. Over. And the same way, you put your thoughts into multiple things. So till now you had only projectile motion method in your head. Now you think, okay, I can also use energy method, right? Now take another problem. Write down this problem and tell me the answers for it. Tell me the answer for these questions. Use any method you want, preferably energy method because that's faster normally. All right, here's the marker again. I toss a marker at 10 meters per second and it goes until a certain height and before coming back. How high will it go? The question is, how high will it go? I toss it up with 10 meters per second. And how high will it go? Any questions on this one before? All good? By the way, for semester 1 exam, watch out for a review video on Rockspace, right? So I'll be preparing, I'm not prepared yet, but I'll be preparing a video of, going through some of the concepts like saying, you should know how to do this. You should know this concept. You should know how to apply this equation. Reminders for the questions that are on the semester exam, right? So once you go through that, you can make your own formula sheet. You can bring your own formula sheet, but it should be just a note card. Put all the formula on a note card and bring it. There's
So they're
absolutely.
not going to be on the test.
What's it?
The formulas aren't going to be on the test.
It's better that I throw it to you because I'm putting the video up anyway.
Yeah.
And when the video, you can see me writing stuff, highlighting the important equations or how to do them or what is the concept behind something. So you keep taking notes and that should be a good enough thing. But don't stop there. Just find out what else is there in the book. Okay. But the focus should be more on the semester exam because I'm touching all the points right there. Yes.
Can we have constants too on the note card, or are those going to be on the test, or
Constants like.
G? Well, I mean, I know G.
Oh, you mean capital G?
Yeah.
Yeah, capital G. Yes, you can have. Yeah. I can write it down on the board if it is needed. So I'm here. All right. Did you find the answer for that question I gave you? Again, the question is this. I throw the marker up. At 10 meters per second. And the marker goes and then stops and then returns back. So my question is, how high did it go? So again, you can tackle this problem by two ways. One by equations of motion. You can use equations of motion like, what's the initial velocity? 10. What's the final velocity? 0. What's the acceleration? Minus 9.8. And going that approach, you can solve it. But the other way of solving it is by using energy. What energy did I give the marker here?
10 meters.
Kinetic energy, right? Which is half mv squared. That's what I provided the marker. And as it went up, it was losing this kinetic energy but gaining. So over here, it gained potential energy equal to just mgh because h is the height gained. So equate this energy with this energy and you're all set. So mgh is equal to half mv squared. M cancels off, which means whatever I taught doesn't matter here. And so solve for v. So 2gh is equal to v squared and v is equal to square, which is
Software H, just
You're solving for H.
Yeah,
Yeah, it's, okay. It's solving for
V
H.
is 10.
And so substitute, so V squared is 100 over 2 times 9.81, and the answer is
5,
it 5.1?
5.09. So yeah.
It's 5.1 meters. 5.1 meters. Now, let's go to reality. The reality is, this market won't go to 5.1 meters.
Air resistant. Air resistant.
So now I'm telling you, this is the reality. I throw it at 10 meters per second, it goes to a height of 3 meters before returning. That is the reality. That means in real, it only goes there and then comes back. So my question is, what's the average force of friction?
Oh.
Average force of friction. So what are you going to do now? Half mv squared. That is the kinetic energy here. And of course, I have to tell you what's the mass of the marker. Okay, so then only you can actually figure this out. So half mv squared here, mgh here. Definitely this mgh is not the same as what this one is. So let's say the marker weighs 50 grams. Okay? So if it is 50 grams, half 0.05 times, what is this, 10, right? 10 squared. That is the kinetic energy I gave here. How much is the potential energy? 0.05 times 9.81 times 3 meters. So definitely this is smaller than this. And the difference is equal to the work done by, which is given by what formula? FD. FD. D is how much? 3. 3 meters. And so you can figure out the force.